So this is a continuation of Devendra's presentation on completely randomized designs, and we will just go straight into a recap. So ANOVA determines whether subgroups of a sample population have different effects on an observation. Recall that ANOVA considers a population sample divided in subgroups. For example, given a study of the effects of 3 different diets on body weight, you're going to use ANOVA to determine whether a treatment has an effect by analyzing how different the mean mu sub I of each treated group is from the population mu. And what do we mean by this? So we compare each data point, y sub ij, with respect to the mean of its subgroup I by introducing the term epsilon sub ij, which represents the difference between the value of y sub ij and the mean mu sub I. And similarly, we compare each data point y sub ij with respect to the total mean mu by introducing the term alpha sub I, which represents the difference between the total mean mu and the mean mu sub I of the group I. I also just want to highlight in this slide that there's a difference between theoretical values and the values we obtain from the data, which we denote with the hat, for example, mu hat. And this is also something to note when we apply these formulas, that the values we obtain from the data are only an estimation of the true population value. And you can calculate these values using the formulas shown here. And we use these estimated values to define the F statistic, which is central to ANOVA. The F statistic tests the null hypothesis H0, that there is no difference between groups, meaning that alpha sub I is 0 for all groups I, while the alternative hypothesis H1 says there's a difference for at least one group, meaning that alpha sub I is not equal to 0 for at least one group. And the F ratio is shown here, which is the mean square for treatments over the mean square for error. And you can see that the mean square for treatments is dependent on alpha hat sub I, and the value of mean square for error is dependent on sigma hat squared. So we'll see in the next slide that we want the value of F to be much larger than 1 to reject the null hypothesis. ANOVA works in testing the null hypothesis due to the expected values for the mean square, where the expected mean square of errors is sigma squared, and the expected mean square for treatments is sigma squared plus this value. And in simple terms, this just means that the mean square for treatments is always going to be larger than the mean square for errors. So F is larger than 1. And in this table, we can see that if alpha sub I is close to 0, then the F score is close to 1. And on the other hand, if alpha sub I is far from 0, then the F score is much larger than 1. So we can use the value of F as a proxy to see if the null hypothesis H0 is true or not. And specifically, we want to reject the null hypothesis H0 when we see that the value F is much larger than 1. But as we can see in the formula here, alpha sub I is not the only parameter that can influence the value of F. And for instance, making sigma square vary will also make the value F vary. And here we can see that making the value of sigma squared smaller will make the value of f larger than 1, meaning that we create a scenario in which we can reject the null hypothesis. And it's important to note that this relationship between f and sigma squared does not contradict the meaning that we attributed to the value of f in relation to the value of alpha sub I. And as illustrated here, we can see that decreasing sigma squared can be seen as increasing the gap between the total mean mu and the means mu sub I of the groups. So we talked about how comparing f to 1 allows us to reject the null hypothesis or not. And the rejection of the null hypothesis depends on how significant we want our test to be. Depending on the strength of significance that you want, you compare the f-score to a certain critical value. For instance, this is the table for significance associated with the p-value of 0.05, and we determine the critical value by knowing the degree of freedom, g-1, and n-g, by looking at their intersection in the table. And if f is below the critical value, then the test is not significant. And on the other hand, if f is above the critical value, then the test is significant and we can reject the null hypothesis. So we use side-by-side plots to visualize the residuals associated with the mean square of the treatments and the mean square of the errors. And we use these to visualize how different the means of each group are by plotting the values alpha hat sub I next to the errors r sub ij, which is the difference between the data y sub ij and the mean mu sub I hat of its associated group. And in this side-by-side plot, we plot the values alpha sub I in one column and the errors r sub ij in another column. And these errors basically give a standard that gives us an idea on how far alpha is from 0. And this slide gives us another way to look at ANOVA, where instead of presenting the F statistic as a simple ratio, we can express it in terms of a difference. And we interpret this difference as a comparison between two models, the reduced model and the full model. And specifically, the difference shown here compares the reduced model, which uses the data y sub ij and the total mean mu, and the full model, which uses the data y sub ij and the mean mu sub I of the associated groups I. And we see the reduced model as assuming that all treatments have the same expected value mu, while we see the full model as assuming some treatments may have different expected values mu sub I. And this idea of presenting ANOVA as a comparison between two models is used, for instance, in dose-response modeling. As shown here, the measured data y sub ij is modeled as a polynomial equation that we obtain from a regression analysis. But regression analysis will always try to fit the data one way or another, and it's important to criticize the relevance of the coefficients theta k returned from these regressions by using F statistics. And we use F scores to determine whether certain coefficients, theta k, should instead be set to 0. And to do so, we use the interpretation of ANOVA seen in the previous slide where we compared two specific models. In the present case, the two models are the model for which the value of a given coefficient theta k is 0, and the value of the model for which the coefficient theta k is not 0. And we can use the associated F score to determine which of the two scenarios is more plausible. And this last slide just summarizes some history surrounding ANOVA. So for instance, Legendre and Gauss pioneered the least square estimation. And after ANOVA was established, you have, for instance, the establishment of linear models by Scheffé. And here we also have in 1985 the drug response regression that we talked about in the previous slide, which was pioneered by Weisberg. So that concludes this summary of Chapter 3, and thank you for your attention, and please feel free to ask any questions to clarify.